So that's why you said it was a 10 out of 10. You just wanted to prove Monica wrong, was it?
Yeah.
Disgraceful.
I was wondering, because you didn't give us the formula of n, the ratio.
Yeah, so I wasn't expecting you to use that.
Yeah. So, if we had to use that formula, then I was going to blame you. But
Why so much hatred towards me? Alright, continuing. Some of you are learning faster than others. Right. Lee, be quiet. Thank you. Jerry, the next time he talks, can you hit him on the back of the head? Thank you, Jerry. Thank you. And if he continues to talk, all three of you, bunk, 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 one after the other. Thank you. And then I'll come along. You regret that. Okay. So in semester 1, we had a problem of solving cubic equations. So for example, ax cubed plus bx squared plus cx plus d equals 0. How did we solve cubics? What was our method we used in semester 1?
guess I thought equal.
Yeah, guess. So first you would start with 0. Then you would try 1 and minus 1 and so on. So what's the problem with this? Yes.
I have a shortcut. You can use calculator and see.
So if he talks again, you hit him. And if he asks me a stupid question, you hit him. Huh? And Monica, if he looks like he's about to do something stupid. Okay. So of course, a problem with this method, a big problem, is what happens if one of the roots is 296? How many attempts would it take? Or let's just even say 250. How many attempts would it take to get here?
This is the sort I say, use 500.
No, but I want to. It takes 500 attempts. Or 501, yeah. What about if the root was 250.62? Yes, but you can't actually find it through this method.
Actually, you can.
You can, but it would be quite a slow process, because what would happen is you keep guessing values, and then you get smaller and smaller and smaller. So then at 250 you get a value, and then when you try 251, you're negative, so it means you've passed it. So you have to go back, and maybe you try 250.5. Are we too big or too small? Too small. So then you have to try 250.75. Do you get what's happening here? Yeah. This process is no good, because it will take you too long to find a root. So there is a better way to do it. And the power of this Newton-Raphson method is that even when you guess the wrong root, you can use the wrong answer to inform you of a better guess. And we'll explain how. So in other words, there's no bad answer, because each bad guess brings you closer to the right answer. It's as if you're asking questions, and each time you get it wrong, you are actually moving closer to the right answer. So it's actually a very, very, very powerful method. Let's see exactly how it works. So let me just draw some. Oh, and of course it's not only for cubics, actually, it'll be for any graph. So let's see how it works. So we'll start off with something simple, like just say a quadratic, like that. And we'll call this y equals fx. And we begin by guessing a value for the root. So we start off by saying maybe the root is at x0, and I'll put x0 here. Now, is that the root? No, it's not, because the root is right there. So, what is this point here? This is the point x0, y0, or f x0. Now, you really wanted this to be 0. It would mean you're at the root. Is it 0? No. So, we failed to get the root, but that's okay, because there's a trick now. What you can do, woohoo, that's a new thing, I don't know how I did that. What you can do is draw a tangent line at this point that you just found, this wrong point. So this is wrong. Now if you find this line and find where this line crosses the x-axis, which is actually a very easy problem to do, this new point is closer to the root than the last point. So let's see a formula for this x1. Okay? So, what is the slope of a line here? Y equals mx plus c. What's the m?
Negative, positive.
No. How would we find the slope of a tangent?
X0 over x0.
No. How do you find the slope of a tangent? Derivative. Oh, sorry, I meant that's the m, sorry.
Yeah.
F derivative x0 x plus c.
Yeah.
Okay, we need to find the c. How do we find the c?
When x is
From the point. Do we have a point? We do. We have this point. So we have f x0 equals f derivative x0 plus c. So c equals f x0 minus f derivative x0. Now, we have this formula. Y equals m x plus c. Let's remind ourselves, what point are we looking for now? We're looking for x1. What's special about x1? It's where the tangent line crosses the x-axis, so it's the root of the tangent line. How do we find the root from this?
0.
What's 0?
Y.
Yeah, so we make this 0. So now we have 0 equals f derivative x0, and I'll call this x1, because that's the point we're looking for, plus fx0 minus f derivative x0. So rearranging this, I get f derivative x0, x1, equals f derivative x0 minus f x0. Finally, I divide by the derivative and I get this formula. x1 is x0 minus f x0 over f derivative x0, where x0 is the bad guess and x1 is the better guess. So even though you can make a bad guess, by using this formula, you have a better value to try next time. Let's see this in action before we talk about it more, but I'll need you to write this down. Yeah.
What if our bad guess is in between the U-shape and we get even worse?
No, like it started here, okay? Or like, we'll put it here for example.
Yeah.
We draw the tangent line, and the tangent line would take us back here, and then we go up, we could go here now. Even if
in the middle.
If it was exactly in the middle, that's a problem which we'll discuss in a moment, okay? So again, Christy?
The x1 equals x0 minus.
It's a formula, but I'm going to add something to it in a moment.
Yeah, I mean, it looks the same.
Yeah? Yeah?
No, I didn't mess it up.
Is this two factorials or is there application?
Let's have a look at an example, yeah. Okay. Where is Sean? And yesterday? Was he late for physics or some class yesterday? Or Monday he was absent? I thought he was missing from one of my classes. No? Well, he comes in late in the morning. He's absent all day today. And you hear from him? No? Nobody knows? Okay. Continue? Right. Now, let's have a look at this. Let's try an example here. Let's say I have this, x squared minus 4, and I want to know what's the root of this. Well, we know what the answer is already. What is it? 2, or minus 2. We'll say 2 for the moment. So let's say we make a stupid guess. Let's say, we'll try x equals 5. Now, of course, that's wrong. If you try 5, what you'll get is 25 minus 4, which equals 21, which is definitely not 0. But Newton said, well, we have a better value now for our next guess. So we tried this, but now instead we should try, according to this formula, 5 minus 21 over the derivative. What's the derivative here? 2x, and the x we said was 5. So that's 5 minus 2.1, isn't it? So what's that now? 2.9, isn't it? Now that's actually, getting close. But then you realise something. Why stop here? Why not start the process again, but this time use 2.9 as the guess? And so what we can do is we can change this into a formula where we keep applying it to get closer to the answer. So we can write the formula now like this. xn plus 1 equals xn minus fxn over f derivative xn. This is the Newton-Raphson formula. So let's apply it to this example. According to this example, xn plus 1 equals xn minus fxn over the derivative. Like that. Right. Let's try this. So, first I started with 5 and then I got 2.9. Let's see what happens if I use 2.9. 2.9 minus fraction 2.9 squared minus 4 over 2 times 2.9. And now I get 2.13. So what's happening? I'm moving towards the root. But is there some way to type this into the calculator so we can automatically put the answer into the next calculation? There is, watch. So what you do is you put in the value you want to start at. So we'll say we started at 5. So I hit 5, enter. Now what happens if I press A and S? What number do I have? 5. Okay, good. So if I type in 5 minus fraction 5 squared minus 4 over 2 times 5, I should get 2.9. I do. But now that my answer is 2.9, that means in this formula this has been replaced by 2.9. So if I press equals again, I now get 2.13 or something. If I press it again,
I'm press again.
So it's moving in, hits the point. So after five or six guesses, I've landed at the root. Yeah, but what you realise is very powerful about this is because you have the product, quotient and chain rule, it's quite easy to know what the derivative of a function is. So basically, once you know the derivative of a function, you can use this formula to zoom in on the point. Yeah. Now, but wait, before you write that down, let's say I pick some ridiculous first guess. Let's say 100,000. Okay, let's go back. Right, so I start at 100,000, and the formula says, no, try 50,000. So, okay, try 50,000, doesn't work. So, okay, try 25,000. Okay, try this. And it's jumping down, but as it gets closer, it starts to slow down, and it reaches the answer.
Okay.
Again.
What if press more and more?
Well, because of rounding, it's actually not quite 2, but the rounds off to like 9 decimal places, it hits 2.
After 2.
No, nothing's happening now. Yeah. Let's start at 1,000,000. 1, 2, 3. 1, 2, 3. Okay. Now, if you started at 1,000,000, it would take you 1,000,000 minus 1 steps to get to 2. But not using this method. Took me like, 10 steps or something. Very, very powerful method. Yes? But there are, of course, limitations and disadvantages. So one disadvantage is that it only gives me one root. Whereas we know my example had 2 roots. Another disadvantage which Lee actually noticed earlier is what? Yeah, and how does that happen? Well, if you have a graph like this, here are the roots. So if you start here, that's fine because you go up, down, up, down, up, down, and you move in on the point. If you start somewhere here, that's fine. So even if you start out here, you go up, tangent, come down, go up, tangent, come down, and so on. But if you were unlucky to start exactly at the turning point, because this is a turning point, its derivative is 0, it means you get a parallel line and you never cross the x-axis. Basically, you have a problem because this piece here is 0. But that would be very bad luck that you hit a derivative, a turning point. Of course, another disadvantage is the formula doesn't know if there's no root. So if there is no root and you try to use this formula, it would simply be stuck trying to find a root it can't. And the formula doesn't know that there's no root. Yeah. Let's try this now with a harder example. So if I said to you, solve EX equals X. What would happen if we tried to solve that? So what could we do first to solve that? You could put log. Yeah, so you would have X equals log X. Okay, how can I cancel the log? I could put an E. So I'd have EX equals X. I'm not making much progress. In fact, we can't really solve this because any time we try to cancel the E, we get a log. We try to cancel the log, we'll get an E. So we're stuck, but not for the Newton-Raphson, because what we can do is change this problem into this problem, and then by calling this f of x, the problem now is to find the root of this. So Newton-Raphson said, okay, well, the formula will be xn minus exn minus xn, and the derivative is exn minus 1. Let's hit that into the calculator. Okay, so we need to pick a number to start with. So we need to make a very, very rough guess at what the answer is. So we just roughly guess in our head. I think it'd be smaller. It could be 0, because if we put a 0 here we get 0, and if we put a 0 here we get 1. So they're not equal, but they're close. So 0 would be a good starting point, 1 would be a good starting point. So I'll start at 0.5. 0.5. Okay. Answer minus fraction e power answer minus answer over e power answer minus 1. So we've jumped to the negative, we've jumped back to the positive, back to the negative, positive, not negative anymore, so I feel like we're zooming in on a point. Whoa. So I think actually what could be happening here is, I don't think there is any, I don't think there is a root here. I think I need to pick a different example. How can I change this a little bit? Yeah, I might, if I put a 2 here, let's just see, 2, 2, 2, 2, 2. Okay, let's just see if that fixes it. Like this. Come on. Get there. You can do it.
Did you put e power to x?
I did. I changed it, but this also doesn't look like it has a root.
Yeah, it's floating.
It's floating? Okay, let's do a different one. Instead of e, I know this one works. Sin x equals x. We'll try that one. So we have fx equals sin x minus x. So xn plus 1 equals xn minus sin xn minus xn over cos xn minus 1. And we should be in radian mode because that's the normal mode.
Could we solve this to GP?
One sec.
Geometry?
I shall answer that in a moment. Let me just type this in. Sin answer minus answer over cos answer minus 1. I start with 100. It's totally ridiculous, but I'll start at 100. Okay, try this. Try this. Try this. Try this. Keep going. Keep going. Oh yeah. What's happening? What's it going to be? Think about it. What should the solution be? No?
0.
Yeah, 0, because sine 0 is 0 and 0. So 0 is going to be solution. And you can see I'm getting closer and closer to 0 then. But what about this one? Cos x equals x. Well, is 0 going to be the answer here? No. Because if I put in 0, I get 0, and here I get 1. So it's not going to be 0. Is it going to be 1? Well, if I put 1 here, I get 1, and if I put cos 1 here, I don't get 1. So take a minute. Tell me what the solution to this equation is. Solve this. Yeah, Andrew, could you stretch over into this? Thank you.
I didn't get 0.
But Lee, there's actually another answer here. So 0 is one of the answers
By
for sine x. Yeah, but there's actually a second answer which is not 0. Is this the answer you stumbled on?
No, it
Alright.
just keeps jumping.
Okay, let's have a look here. So what is the Newton-Raphson formula for this one? Xn minus cos xn minus xn over minus sine xn minus 1. Alright. Let's try and at least start at a reasonable answer. So 0 is not going to work. Let's start at 1. Okay. Minus cos the answer minus the answer over minus sine the answer minus 1. Okay. Oh, got that really quickly. This is the answer. So in other words, if you have this equation, cos x equals x, then the solution is x equals about 0.739. No, this is I don't know. No, it's not any proportion of pi. So what is cos of 0.739? 0.739. Right. I start with 1.
It has to be a radian one.
Yes. Yeah? Now, why are you asking about GP?
Although it's slightly the same, the formula.
Okay.
So I actually can read this.
Now, before we continue any more with this, it would be good to ask ourselves, how can we know that there's a root? Because you noticed earlier, which I totally did on purpose to show you, that sometimes there is no root. And we'd be wasting our time. So how can we know if there is a root? Is there any way we can check if there is a root? That's only for quadratic. So one thing you could do. Right hand rule. I'm giving you the right hand rule and the left hand rule. Okay. Right hand, left hand, and the grip rule. All three of them. Okay. One way you can know if there's a root is if you think there's a root between, say, A and B. If you think there's a root between A and B, what you can do is you can calculate f of A, you can calculate f of B, and if one of them is positive and one of them is negative, then you know there must be a root. This is how you can check.
Okay, well that's for A and B.
Well, this is the thing, you have to make some kind of a guess at the beginning. So, for example, if I have a cubic, I know my cubic looks something like this. Because I know it goes this way and this way, I could guess something like minus 1,000 and plus 1,000. This will probably be negative and this will probably be positive. So I know there's at least one root in between. Now, of course, if you have a quadratic, you have to have at least some rough guess at where the root could be. In the exam, what will happen is that they'll say, show that there is a root between 2 and 5. So then what do? You calculate f2, you calculate f5. One should be positive and one should be negative. If they're both positive and if they're both negative, does this mean that there's no root?
No.
Not necessarily, because you could have something like this. So if you put your A here and your B here, this will be a positive, this will be a positive, and you've missed many roots. So in other words, if FA and FB differ in sign, then that means there's a root somewhere between A and B. But it's important that you understand that this is not true. Or rather, I should say I should say that the opposite is not true. it's not right to say if there's no difference in the sign, then there's no root between A and B. This is not true. It's only true to say if there is a difference in the sign, then there's definitely a root. But if there's no difference, we don't know. Okay? So this is very simple, but a very useful way to check if there's a root. But I think KJ, as you just said a moment ago, or somebody said a moment ago, you need to have at least some idea of where to draw your A and B, roughly. So for example, in my question with sin x minus x, if I put x as 0, cos x minus x, if I put x as 0, I get 1. And if I use 1, what do I get if I use 1? What's cos 1 minus 1, please? Is it a negative?
Negative.
Yeah, negative. So I would know that there's a root between 0 and 1. So what would be a good place to start if I know there's a root between 0 and 1? Maybe I should start at 0.5. You know? And then you can move in quickly. In fact, the true answer was 0.73, so I would have got there very quick. If you have a cubic, there is another way to know how many roots you have. So think about this. If you have a cubic, you can either have 1 root, 2 roots, or 3 roots. Now, how can you know which one you have? Well, if you find the turning points, the derivative of a cubic is quadratic. Is it easy to solve a quadratic? It is, because you have a formula. So can you easily find the turning points? You can. If both turning points are above the x-axis, then we must have only 1 root. If one of the turning points is above the axis and one of them is on the axis, we have 2 roots, and we've actually found one of the roots accidentally. If we have one turning point above the axis and one below the axis, then we know there must be 3 roots. It's the only way to draw the cubic. We can't draw it any other way. So by knowing the location of the turning points, we can work out from the graph how many roots there are. We sometimes get this in the exam. It might say, show that this cubic has 3 roots. So that means find the derivative and the turning point and show that one is in the positive and one is in the negative. Then you know you have 3 roots. Yeah? So make some notes on this if you need to. I don't know what you need to write down. What? Oh, my beautiful English.
Teacher, I don't understand what is FA and FB different are.
Yeah, if one's a positive and one's a negative.
So what is FA and FB? The Y of this.
Yeah?
So we have a question like number 1, number 2. We can use calculator.
Which one?
How many zeros do each have?
No, off my heart. Literally, Chrissy, what I just showed you is how you do number 1.
Yeah, but.
You have to find the turning point.
Yeah, but.
No.
That's never.
No. Number 2, how do you show that there's a root between 2 points? Yeah, you would, for example, in 2a, what would you have to calculate? F0 and F3. In number 3, I actually tell you to use the formula twice only. In number 4, I say in each case prove there's a solution and then find it. In number 5, I ask you to find a value for the square root of 2. Number 6 is an equation to solve. And number 7, you might then start to wonder, okay, I want to know how many times I need to use this formula. For example, maybe you don't care about finding the exact answer. Suppose the answer was 1.23456 and you only need three decimal places. So you're happy if you can get to 1, 2, 3, 4. And you want to know how many times do I need to use the formula. I actually said there's a way to know this. You can use this formula I gave you in question 7. If you calculate log base 2 b minus a 10 to the power of number of the decimal places you want, that's how many steps you would need. So for example, where's it gone here? Here in this one, we know there's a root between 0 and 1. And suppose I want my answer to 2 decimal places. How many times would I need Newton-Raphson? I would need it log 2, 1 minus 0, 10 power, what did I say? I wanted 2 decimal places, so 2. 1 minus 0 is 1. 10, 2 is 100. 100 times 1? 100. Log base 2 of 100. 2, 4, 8, 16, 34, 128. And I have to round it up because I can only use whole numbers. So if I use the rule 7 times, I'll definitely have it right to 2 decimal places. Now, I'll actually be better than 2 decimal places, but it will be at least 2 decimal places right. Now, you don't need to know this rule for the exam, but if you're wondering, yes, there is a way to know beforehand how many times you need to use Newton-Raphson. And you realise that if you can get your A's and B's closer together, then you can make this smaller, and you can make this smaller, so you need the rule less. So it's good to be close to the answer to begin with. It means you might need the rule less times. Yeah. Newton-Raphson is very, very important, especially in modern engineering, because a lot of engineering equations are so difficult you can't solve them using algebra. You'll have to use a computer, like your calculator, in a process that gets you closer to the true answer. So a bit like you were talking earlier about your simulations and so on. If you were to write the equations out to describe these problems, they would be very complicated. The only way to solve them is what we call by using a numerical method. Has anybody seen this method before in school, or is this a new method? It's new?
I saw that formula, but I don't remember it exactly. Will you use that on the other part?
I don't think so. It can only really be used in this way, I think. Yes? Okay, I want you to try some of these questions now. Say again?
That formula you taught us, or we use that, is it possible to use that to find the inverse function?
Oh, use Newton-Raphson?
Yeah.
In a way, yes, I suppose you could.
I thought I use that to find the inverse function?
No. You could slightly change this formula to use to find the inverse.
Who's Raphson?
Huh?
Who's Raphson?
I don't know, but whoever he is, he must have discovered this formula at the same time as Newton, so it's named after both of them. But independently. But of course, poor Raphson, this might be the only thing he's famous for, and nobody knows who he is, because Newton got his name to it. So of course, if something is Newton-Raphson, it's like, who the heck is Raphson? Can I close this screen?